Okay, good morning. If you are joining the recording, I guess I don't know. I shouldn't say morning, but I'm doing a little volume check, and just wanted to comment that there is a warm up. It's been a while since there's been a warm up. That's why that happened. I see. That makes a lot more sense. That makes a lot more sense. Okay. Good morning, folks. All right. Okay, so good morning. We are starting a new section. So I recognize that optimization is kind of a beast because, well, it is. There's no ifs, ands, and buts about it. You're taking the ideas of word problems from an algebra class, and then it's kind of going up one level. And that's I I think it's important maybe to just recognize that and say they can be frustrating questions. Um, and one option is to give up. I hope that's not the option you take. I hope the thing that you do is you say, I need to work on this. It's going to take some failure as part of the process, and then deciding, you know what, I've had enough. I'm gonna get help. I know that the online thing makes it all that much harder, but those who have the few in this class who in calculus who have visited my office hours, I think have I've asked every time, is there anything that could have been done, that do you understand the problem as you leave office hours? And I believe in 100% of the time I've gotten a yes. I don't know if it's out of politeness or something like that. I have had a lot of visitors for my 11 a.m. More advanced class. But that said, the office hours are yours too. And if I get that, like, even though I'm holding the same times, if it doesn't work timing wise, because you've got other things going on, I know that lives are totally interrupted by this. Just email me, set up an appointment. I mean, I know I talk about like having other responsibilities myself, but I will, if you ask for time, I will make it happen. It might not happen literally that same day because there might not be any time on that day, but we will find a time to meet up. I think this quote is actually maybe very um, appropriate for talking about um, what's going on with optimization. So hang in there, I guess is what I'm trying to say. Like this process is not easy. It takes work. I wish it didn't, but the more realistic word problems are, the the more challenging that you're going to see some of those kind of features. Like that's kind of how things go. So what I'd like to talk about in this warm up. Sorry, I was stalling, hoping that you might look a little bit at the warm up here. It's this is backwards now, right? So it's not. There's this function, okay, 10x to the ninth, but the question isn't go take another derivative. If you were to take a derivative, then you'd get 90x to the eighth, of course, right? Using the constant multiple rule combined with the power rule. But the question here isn't to take a derivative. The question was, it seems like this function, the 10x to the ninth, is the result of having taken the derivative. You see what I mean? If taking the derivative is going forwards, let's go backwards, right? And it looks like this 10x to the ninth was produced from the process of having taken a derivative. It does look like that, right? And so what what I'd like to do is kind of keep doing that each time. And then this next one, if somebody took the derivative of something and then got x to the fifth, well, that one's a little harder, but we can think through that. Like there's going to be some constant in front that's got to kind of fix something, and we'll figure that out. And then the next one, the third one, is hopefully nicer again. Something was differentiated, and then the result was 8 to the x times ln of 8. Can we go backwards? So somebody did the forward step, like before spring break, we had an exam on differentiating going forward. But what about going backward now? So that's what I'd like to address in these warm-ups. The warm-ups are meant to provide sort of the theme for what we're doing today, and then we'll, after the warm-up, kind of sort of be better set to think about this kind of going backwards business. So yeah, big story today. If differentiating, the thing that we've been doing kind of all semester long from like say the third week when we introduced derivative all the way up until yesterday when we applied the derivative for optimization problems. Now the goal, if that's forward, now we're talking about undoing the derivative or going backwards. So the warm-up is at the top of this slide again. And so just to word it a little differently, just to make sure, right, the point here is to say the derivative of is 10x to the ninth. I hope I've stalled enough, maybe almost out of annoyance, that you might have thought, okay, the thing that was differentiated was x to the 10th, right? That would be 10x to the ninth. So it's the first one. And I'm going to stop talking for a minute to pause long enough for the internet so that you get that. And if you've got a question, got to take the first one slow. And if we're cool, then we can, I don't want to lose you on the first thing we do today is what I'm trying to say. So let's just wait. If you've got a question, ask it, because it's the whole idea behind today is to go backwards from the derivative. Okay. So the next one's a little harder. Actually, before the next one, I have I'm seeing on my other screen where I have the slide already revealed. I want to remind you of some notation. So one way to indicate the derivative is this d over dx thing. I know that we're used to writing the prime a lot more. I like the prime more too, if I admit it, because it's much easier to just write a little tick mark. But for what we're doing next week, it's going to be kind of important to remind you that there's this other notation for derivative. So it looks kind of funky. D over dx is the way to say derivative, but this is derivative of x to the 10th equals 10x to the ninth. So say it with me. I mean, you don't have to. I guess you're muted, but like just, the derivative of x to the 10th equals 10x to the ninth. That's what you should be thinking when you write that or when you read that. An incorrect version of this would be missing this d over dx or missing a prime altogether. I have seen people write x to the 10th equals 10x to the ninth. Those things are not equal. It's the derivative of the thing on the left side ends up being the thing on the right side. So don't say these functions are equal. They're related. It's the derivative of the left thing is the right thing. So I put surrounding sad faces. It's in red. The next one's a little more tough. What should be differentiated to produce x to the fifth? Well, take a look at what would be the derivative of 1 over 6 x to the sixth. So if you take the derivative of 1 over 6 x to the sixth, now the 1 over 6 is the number. So there's no need to, even though it's 1/6 times x to the sixth, you don't need to apply the product rule. You could, but because it's just a plain number, it's much more convenient. It's much lazier to just and a good lazy to just apply the constant multiple rule. So you copy the number 1/6, and then you differentiate 6x to the fifth. Sorry, differentiate x to the sixth, which would give you a 6x to the fifth, and then the sixes would cancel, right? The 6 in the denominator would cancel with the 6 in the numerator. And so then you'd end up with just an x to the fifth. So as far as what was the original function before differentiating, you could write it as it is in the square brackets here as 1/6 x to the sixth, or another way to write this in algebra is x to the 6th over 6th, you recall. The third one, what is h of x? So what had to be differentiated in order to get 8 to the x times ln of 8? And here, this is a reminder of the exponential derivative rule. So this could have been stated, like I think the end of the fifth week or something like this, that the derivative of 8 to the x is 8 to the x times ln 8. So if the result after differentiating, notice there's a prime here in the question, h prime of x is 8 to the x times ln of 8, then h of x, the original function here, would have been 8 to the x, right? The last one is more challenging, but it has sort of the same ideas as the second warm-up question here. So I'd like to work through this one a little more slowly. So in brackets here, 1 over ln of 3 times 3 to the x. Let's take the derivative of that function. So first, copy the 1 over ln 3 because it's a number, and then 3 to the x differentiates to 3 to the x times ln of 3. Now here, the ln of 3 in the denominator, ln of 3 in the numerator cancel, so you end up with 3 to the x. So after it's all simplified, differentiating what's in the square brackets gives you the 3 to the x. So that's, what did you differentiate in order to result in having a 3 to the x? In this case, it was 1 over ln of 3 times 3 to the x. I want to double check for that last one, which usually is the one that ends up being rather confusing. So I'm just trying to anticipate the question that might come up. And I'm just going to remind you that ln of 3 is a number. ln is a function, but once you feed in that number 3, then ln of 3 is just a number. You type this into a calculator, you get some decimal. If this ln of 3 is a number, then 1 over it is a number. And so the whole point is I wanted to remind you of the constant multiple property, that if you've got a plain number, plain constant called k, times a function, then to take the derivative, I'm using the prime notation, you copy the constant, there's no prime on the k, and then you differentiate the function. So that's what happened here. In fact, I have some colors. Don't look at the red up here now. I've highlighted the k's, the constants. What I'm trying to say is 1 over ln of 3 is a number. So to differentiate, you copy the constant, 1 over ln of 3, copy what's in red. And then you have to notice what's not in red. This 3 to the x is the f of x here. You've got to differentiate 3 to the x, and the derivative is written there. It is 3 to the x times ln of 3. So let's kind of pause here, see if are we kind of as okay as possible with that, or I'll pause, see if there's any questions that can be addressed. Okay, one last thing for this. I know it's quite a lot of warm-ups all in one, and it's been a while since we've done a warm-up, but I think today the wording of some of these things is going to be important. So this is the content that's already kind of up here, but just with slightly more notation to include the f prime of x. But I think this wording is not surprising to you, right? The derivative of x to the 10th is 10x to the 9th, but we're going to kind of run with this. In fact, I have this at the top of the next slide. Okay, so there are two main notations we've had for it. So this is also copied from previous slide. This d over dx, again, please, you don't do yourself any favors if you just kind of try to write things without thinking about what it means, right? Like it's helpful to always think about what things mean. So this d over dx is derivative of, say that. Same with the prime. When you see the prime, think derivative of. Without the prime, we have a problem here, right? Without either at least the prime or the d over dx, one or the other. So there's these two ways of writing the same fact that in the first bullet is written just kind of more in a sentence format. But now we dig into some of the real issues for today, which is what is another function that differentiates to 10x to the 9th? Now this question sounds strange. So you're like, wait a second. We just provided in the first warm-up, we provided as our answer, x to the 10th is a thing that you do the derivative process and you get 10x to the 9th. What do you mean? There's another function that you can differentiate to get 10x to the 9th? There's another function you can differentiate? What else is there besides x to the 10th? Like, that's the only thing you would prime to get 10x to the 9th, right? And it turns out that that's not the case. Really? Really? So my hint, I want you to think about it, so I'm not going to reveal things right away. But my hint is, let's say you had a new function here, g of x. This function is 1. I mean, I'm not saying g of x is an answer to this question, right? But I'm just asking what is the derivative of this function? If the function is just always producing the same numbers output, it's called a constant function, then recall that the derivative is 0. So how is this strange hint helpful at all in answering the question? So now you've got this function whose output is just always the boring 1. It's the y value is always 1, therefore the slope is always a horizontal line, so the slope is 0. What's another function that differentiates to 10x to the ninth? I want to give you a minute to think about that here. So another function whose derivative is 10x to the ninth. So how does the fact that the derivative of 1 is 0 help? Well, remember we have the sum rule, right? So here it is, I'm revealing. The derivative of the function 10x to the 10th plus 1, right? What would be the derivative of that? Well, the first term, x to the 10th, differentiates to 10x to the ninth. And then we still need to differentiate the next term. We've got to differentiate 1, right? One term at a time you differentiate. But when you differentiate a 1, you just get a 0. So I didn't even bother writing the plus 0. Sound cool? Right? Like, are we... So this provides an answer. It's maybe a cheap shot answer, but it is an answer to the question, what's another function that differentiates to 10x to the ninth? So one possibility is what's in square brackets here, x to the 10th. Another possibility is x to the 10th plus 1. But if that works, let's run with this. Isn't there another possible answer to this question as well? How about what if we took the derivative of x to the 10th plus 2? For that matter, what if we took the derivative of x to the 10th minus 1, 2, 3, 4, 5? Right? I hope you'd agree that what's in the square brackets up here, and then the 3 options for the functions in the square brackets there, all 4 of those functions, when you take the derivative, you end up with 10x to the ninth. I do want to put this in words as well. Not that you shouldn't, if you're taking notes, you should not be no need to write this next block of 3 things in words. I just want you to stare at this block of notation and those blocks of words, and it's just, they're saying the same thing. The notation just takes up less space to write. What we're about to do right now, though, not that you need to write down the next thing either, I just want you to kind of stare at it for a moment, is I'm going to swap this thingy and this thingy. They're going to move places, but you can't just swap them and have something that works. We've got to change up something in order to swap. So not only did I swap, I also used a new word. Okay, so derivative, if derivative is going forwards, this antiderivative is, informally speaking, going backwards. So starting with 10x to the ninth, if you go backwards, if you undo the derivative, it's called antiderivative. One option is x to the 10th plus 1, but it's not the only option. You could have, we saw another way to go backwards for the derivative is x to the 10th plus 2, and another way to go backwards was x to the 10th minus 1, 2, 3, 4, 5, which is also why I know it's a little picky. Over here, the word the is being used because when you have x to the 10th plus 1, what's the derivative? There's only one. There's one correct answer for what the derivative is. The funky thing now is if you start with x to the 10th, 10x to the ninth, and you ask what should be differentiated to give you 10x to the ninth, there's many possible answers, right? Because what's another function? That's why the word "an" is used here, since there are many options technically. Just to make sure and ask, it's really the same question up there, just using our new terminology. So what's another antiderivative of 10x to the ninth? And just to word it in sort of the same language as one of these 3, an antiderivative of 10x to the ninth is x to the 10th plus, and then I just typed on the number pad on my computer. Just some random fixed number. There's no variable over here, right? So the derivative of that part should be a 0. Are we okay with the content of this slide before moving on? I think then the key idea that I want to take is if you look at like these 3, is there a way that we could summarize what's going on because I just gave three examples there, right? Like it could be an x to the 10th plus a 1, it could be an x to the 10th plus a 2, or it could be an x to the 10th plus negative 1, 2, 3, 4, 5. But there's other options, right? X to the 10th plus 28 or whatever. So there's so many options. How can we summarize what's going on here? Because there's not three facts that look like this. There's an infinite number of these facts that look like this. So is there language we can use to talk about this in general? And there is. That's at the beginning of the next slide. So I'm going to write down a thing that's meant to address what's going on here in a way where we can talk about all the options without writing all the options. So if C is a fixed number, I mean, C is a number, like not a variable. Like C is like 25, C is 31, whatever. Like then the derivative of x to the 10th plus a number, just a fixed number, is 10x to the 9th. And then if you swap the order of the two things, then you have to use the word antiderivative instead of derivative. So an antiderivative of x to the 10th, sorry, I keep saying that. An antiderivative of 10x to the 9th is x to the 10th plus that fixed number. Let's say the same thing in notation, because it takes up less space to write using notation. So there's two ways, right? So like what you're seeing here is like the thing boxed on the previous slide. So there's derivative of x to the 10th plus c, and then is the equal sign, and then we have this 10x to the 9th. Of course, another way to write that is instead of the d over dx to use the prime notation. The second thingy here, right? So yeah, so that's that. Maybe I'll just do it this way. Now, okay, an antiderivative of 10x to the 9th is x to the 10th plus c. So this symbol is new. It looks kind of like a stretched out S. And actually, you see also, I'd like to point out there's this dx there. Please write that in right now. Like, that's going to be important. So this notation's kind of strange because the two pieces of it are separated from each other. And then this 10x to the 9th is kind of right in the middle of it. And then after the is, which is the equal sign, you have this x to the 10th here. Now this is too messy. I got to maybe erase so you can see what's going on here. Okay, so this elongated symbol that looks like that, together with a dx, is antiderivative, right? In fact, I have this on the next slide. Or not next slide, sorry, just the next piece of this slide. So when you see this new symbol, actually alongside this symbol alongside the dx, I want you to think antiderivative of. So we have d over dx meaning derivative of, and this new symbol, when you see it, you should think antiderivative of. Let's pause, make sure any questions I can address. It's super important when you see the symbol d over dx to say derivative of, and when you see the symbol this kind of like elongated s or the snake-like thingy, you've got to think antiderivative of. If you don't, you're going to get yourself super confused as we move forward, because in about a week, the problems we look at are going to mix both symbols at the same time. So you've got to be real careful, and it just doesn't help to say, I'm not going to think about what the symbol means. So as you write down the symbol, or whenever you read these two symbols, please think the appropriate phrase, derivative of in the first case or antiderivative of. I want to completely clarify just for sure, because this is, I think, the place where people get the most confused. So I wanted to take these two pieces, I want to put them on the next slide, and I want to color code some things. This is, I think, the best I can do without like writing on a board or something. Is if you have, so I'm not using red to mean wrong right now. I just wanted two primary colors that showed up relatively well on the screen. So if you have the derivative of x to the 10th plus a number called c is equal to 10x to the 9th, then when you look at this symbol, right, this is antiderivative of, kind of alongside the dx here. I know it's kind of strange. This dx seems kind of useless right now, but it will have a role in about a week. Anyway, the two symbols combined, you should say the phrase antiderivative of. So antiderivative of 10x to the 9th is, for the equal sign, x to the 10th plus c. So you'll notice that the two I used the colors to indicate, where the same thing got copied over. And the thing that people have usually found super helpful is if I draw in arrows. So I would suggest doing that as well, right? So if you swap where instead of going forwards, if the derivative is going forwards, if we're now going backwards, we need a new notation for that. And as strange as the notation is, it's this combination of things. Okay, I do want to talk about how to say this this line here in words, and there's two options. You can say the general antiderivative of 10x to the ninth is x to the 10th plus c, and c is a constant, c is a plain number. Or there's this other language we'll use as well. The indefinite integral of 10x to the ninth is 10x to x to the 10th plus c. This if you just want to say antiderivative of in a sort of a more casual way, that's fine. Antiderivative should this anti in front of derivative should tell you go backwards from the derivative, right? Okay, so let's now do lots of examples. Most of class today is meant to just keep doing example after example. So, question. You'll see questions like this in like future quizzes. Like a week from now, you'll see questions like this symbol, which I'll just start using the language integral of 6x to the fifth dx. So the dx, I would say please write down the dx, not please write down, right? I mean, well, please, yes, I'll be kind about it, but like you got to write that. It's people want to leave that out, and you just don't build a bad habit right now. That detail absolutely matters. If you don't start the habit now, you'll get stuck on something in about a week. I before moving on, let's just call it out again just to make sure. Like if people are downloading the slides and not watching because of issues with that, I just wanted to have it in the slide. The notation is strange. It is strange. If you've never seen this notation, it looks strange. The 6x to the fifth is surrounded by that elongated s thingy on the left and a dx on the right. But that's just what's happening. Before answering the question, I also just want to clarify what the question is saying. It's not saying take the derivative, right? If we were saying take the derivative, that kind of going forwards action, we would have had 6x to the fifth with a surrounded in parentheses, then with a prime symbol. That would have been a question we would have asked right after discussing the power rule, like way back, like maybe fourth or fifth week of the semester. This is about going backwards. So the question is asking what function, or actually plural functions, should be differentiated to obtain 6x to the fifth. That's what's being asked here. So in answer to that question, sorry to copy all this text in the question again, but I wanted to now demonstrate where the heck the equal sign goes. Okay, so the answer to this question, what should you differentiate to get 6x to the fifth? It should be x to the sixth plus a plain number, any plain number you want. That's what that C stands for. Yeah, the note that I just made was I wanted to re-include the question in full, just to clarify how the equal sign should be used. I'm modeling how you need to be using equal signs and things I will be expecting to see in your own work in the future. And then just one of the ways to read this is to say the antiderivative, or more technically the general antiderivative, but just casually, antiderivative of 6x to the fifth is x to the sixth plus c. Before digging into more examples, let me try to clarify a very common error that I have seen in Math 175. So in an attempt to answer this question, there's the question again. I have seen people right after writing an equal sign saying, here's my answer, and they'll include this correct piece, this x to the 6 plus c, but they'll still keep this integral symbol, this thingy and the dx. But that symbol shouldn't be included on the right side anymore. Because again, this goes back to this habit that I want you to form of what this symbol means, right? Whenever you see the symbol, I want you to think antiderivative of. So let me point out this in this red box. This is not correct as written. It's That's absolutely incorrect. But let me just, why is it incorrect? What it's saying is, so I'm reading the symbol. I'm trying to model how you should think about this. It's saying the antiderivative of 6x to the fifth is that symbol again, antiderivative of x to the sixth plus c. This is suggesting that this antiderivative of again, meaning that you'd need to reverse the process of the derivative again. So that's not what needs to be said. In fact, to get a correct statement, I copied the previous line and I crossed out antiderivative of. To get a correct statement, it's antiderivative of 6x to the fifth is, and then skip the crossed out text, x to the sixth plus c. That's what this is saying here, right? Notice that after the is, if the correct way to say it is to remove the phrase antiderivative of, to only have x to the sixth plus c, that's why it's just x to the sixth plus c up there. I want to pause. What if it was a double prime? Excellent question. We are not going to go. Yeah, if it was a double prime, sure. But the point is, actually, we're not going to go there. Um, and here's the short reason is when it comes to differentiation, we often take a function and we do a double prime to look at concavity issues. And the reason is because differentiation is actually I would have never said this in the first half of the semester, but differentiation is kind of an easy task in that differentiation may be annoying, but if you're very consistent and you apply the chain rule when you need to and you apply it correctly and the product rule and quotient rule, you can differentiate anything out there. I mean, do you remember that group quiz? You can just there could be a monstrosity of notation and you might want to chew me out for providing something so crazy to differentiate or something like that. But anything can be differentiated, right? If it's written down formulaically like this. The issue is if differentiation is easy, this process of undoing the derivative is a beast. I mean, it can be painful at times. And so therefore, the kinds of questions that are asked in the area can't be so much. And among other things, it is never ever my expectation for you in this class, or when I teach, we have another calculus series where there's 3 semesters of calculus in a row. Even there, no one is ever expected to undo the derivative twice. You only undo the derivative once. So I hope that addresses the what if it's a double prime. We don't even go there because it's too much of a monster, just way too much. Just doing this once is going to be enough work. So I'd like to, I know it's a little awkward, but just kind of give you a moment to practice some questions in class. I know it's been a while since we've done things kind of in that format, but let's just pause, right? Take a couple minutes here, take 5 minutes, take 10 minutes. If you want to check on an answer, you can do that. So it's sort of like I'm walking around the room right now. If you want to type a privately, I will look at the chat boxes kind of on this screen or that screen, depending on which version of me you type to, and I'll try to confirm for you a thing. I will say this though, please try to write using good notation. So meaning right after the question here, put an equal sign, or better would be to rewrite the question as part of your answer to say this equals, because I want you to practice how that equal sign gets used and what correctly needs to follow in the space here in order to do this. So take a moment. At first these seem a little strange, but once you get going, I don't, maybe it won't be too bad. If you want to work in groups, that's another option, meaning you can private chat with somebody else, right? And just say, hey, did you get this? It's an option. I never thought of that until just now, but why not? Sorry for the clicky noise. I'm kind of going ahead in my notes on the other screen to see how we're doing, and we're making good time. In fact, I'm afraid we're going too fast, so. The third question here, I'll just comment, is a little stranger, only because there's no x's anymore. That's just the variables t instead. But just if you want to, for a moment, just change the x's to t's. I mean, the t's to x's and answer the question that way, and then switch them back to t's at the end. That's fine. It's kind of same deal with the last question, I guess, right? So just kind of a poll for a moment. See how we're doing. Can I just get responses from folks in the chat box, like more time, or I'm ready to kind of see the answers? You can also unmute to say it if you want. Okay, I've got one. I'm ready, but I just want to if anybody wants to say I want another minute, I want to kind of meet in the middle when that happens. These are still the usual dynamics of a classroom, I think, still happen. So, okay, I've got another. I'm ready. I'm good. Okay. Uh, there's one other sign. Okay, I got an. I'm ready. And again, it's just like in class. Like nobody should. Yeah, we things come at different times, and you get what I mean here, right? Okay, so I've got here x to the seventh plus c, right? And then the check you can always do is you could always differentiate the thing I just circled, differentiate x to the seventh plus your social security number, and see if you get 7x to the sixth. The next one's maybe a little stranger, but I did try to pick nice-ish enough numbers. So if you differentiate 100x to the third plus any number, then you'll get 300x to the second. This plus any number has to be there. So I keep saying plus any number right now, but if you'll just hear me say c. But if I just say c only, I notice in the past people forget what the heck does that c mean, and then they'll forget to even write it. So the c is required, but it means just any fixed number. The next one, if you differentiate 4 to the t plus c, so t is the variable here, then you should end up with 4 to the t times ln of 4. And then the last one, I know the e seems a little strange and all, but actually recall e to the u is its own derivative. So e to the u plus a constant is its own antiderivative. If that makes sense, right? Like if going forward the derivative is e to the u, then going backward you just get back in e to the u again. But as with all of these antiderivative problems, the expectation is to have the plus c there. So I'll pause. See, are we cool with that? The other, and as I wait, I mean, type a question or say a question if you want. But I guess what I'll also just comment on is you can always check. That's the great thing about these questions. As strange as they are, and as challenging as they sometimes get, you can always check your work. You can always take oh, is this right? That doesn't seem right. You can always just take what's circled there, differentiate, and see if you get the thing between the two new symbols on the other side. So you can always check if your going backwards worked fine by doing the going forwards process, because the going forwards process is way more familiar and much nicer. Okay, so doing this process in this way all the time, this is good to get your feet wet in this, but doing this process in this form where you're always scratching your head to go oh, what do I have to differentiate in order to get that, becomes so much work that it's nice to have rules. So just like we had derivative rules, now we're going to have antiderivative rules. So every differentiation rule has an undoing, an anti-differentiation or an integration rule. So let's start building one of those. So I'd like to notice the pattern. First of all, if you take the function x to the 2 over 2, then plus any old number, any fixed number c, and you differentiate. I didn't write out the work, but let's think about what happens when you differentiate x to the second over 2 plus c. By the way, let's not differentiate yet. I'm going to do an algebra step where I could write this that over 2 as so I don't want to use the quotient rule as my point, as an 1/2 times x to the second plus c. And then when you differentiate the first term, well, there's a constant 1/2, so I'm going to copy the constant in front of the function and then differentiate x squared as a 2x plus. And when you differentiate the c, the derivative of a constant, is 0. So here the 2's cancel. In the end, you're left with x. But I've written it as x to the 1. I put that hidden exponent 1 in because it'll be easier for us to notice the pattern in a moment if we put that 1 there. I will just comment now that what we can do then is we can swap, right, these two things. But when you do that, you need an integral sign. So I wrote this off to the side this way, right? So the side that had the calculus notation over here was by the function that was being differentiated. So now the side that has the calculus notation is the side that has the antiderivative, right? So it's the function that's being differentiated is now on its own side without the calculus notation. So continuing this, if you take the derivative of x to the third over 3 plus a fixed number, you'll end up with x to the second. So swapping the two things, so like that kind of red and blue coloring version that we did at first, you should end up with the antiderivative of x to the second is x to the third over 3 plus c. The derivative of x to the fourth over 4 plus c is x to the third. So the antiderivative of x to the third is x to the fourth over 4 plus c. The derivative of x to the 100th over 100 plus c is x to the 99th, right? So every time you take a derivative, the power lowers by 1. So if you start with x to the 99th and you are asked antiderivative of, then based on the work we have here, the antiderivative should be x to the 100th power over 100 plus a c. So think of what's going on in the power rule. I know this over 1/4 makes the thing you're taking the derivative a little messier, but the power was 4 and goes down by 1 to a 3, right? The power rule always lowered the power by 1. And take a look here, the power starts at a 3 and goes up to a 4. Think, we got to undo subtract 1 somehow, right? And also, you might say, well, why does this look so funky with the fraction? It's because this side is nice. This side is super clean without a fraction, just to have an x to the third. And that's nice to have just that x to the third here. So what I want to do is have you look at these, and now notice a pattern. So the antiderivative of x to the n dx equals, so staring at these, can you fill in? I already started writing a little bit. I'm not done. Just wrote an x, but x to the what power over what, Do you see how, like, if n was a 99, how are we gonna get a nice little box with a formula based on recognizing a pattern up here? Right? Because this box is going to simplify our thought process for this type of antiderivative problem. So I hope what we're seeing is like this, well, look, if n was a 99, but now we need to have the exponent be 100, shouldn't this be a x to the n plus 1? And then that same number, that 100 that's the exponent, also happened to be the denominator. Oh yeah, and then all of these, to keep the pattern, also have a plus c. I'll just advance that forward. I hope that works as recognizing the pattern. Or rather, I mean, we use the pattern. We look at this to recognize a pattern to get to here, but if you want to verify that we did it right, to check our work, you could now treat this formula here as like the standard, and then go back up to one of these and see, yeah, does that work or not? There is this extra little comment here, if n is not equal to -1. So that's required because I have a comment here for it. Why do we need to have n not equal to -1? It's because if n was -1, you would plug in -1 for n, and then that denominator would be 0. So we'd be dividing by 0. So there's like, this formula works almost all the time. You just cannot use this formula if this n right here is a negative 1. But otherwise, this will work, right? So you could use this formula like when n is 1, like over here, or 2, or 3, or 99. So let's do a couple practice problems as a whole group. What I've done is I have copied this box to the top of the next slide for reference. Are we actually, before doing that, I'm going to pause to see on this slide. Are we okay with that? Are we okay with moving forward? Or do we have any questions that can be addressed? Okay, I will move to the top of the next slide. So sorry, like I know the pauses are awkward, but I know from being signed in twice and writing on screen and then seeing what I write on screen like 5 seconds later, it's good for me to pause a little extra longer than feels, yeah, anyway, sorry about that. Okay, so here's a question: integral of x to the fifth, or we could say antiderivative of x to the fifth. We should plug in n is 5. That's okay. N isn't negative 1, so this will work. And plugging in n is equal to 5, following what the formula has, notice there's no integral sign here. So the final result after the equal sign no longer has an integral sign, but we should end up with x to the raise the power up by 1 from 5. N was 5, so n plus 1 is 6. So x to the 6th over, there's an n plus 1 again, and that's 6 here. Okay, here's another one. Antiderivative of x to the 2000. So now n is 2000. That works. At least n isn't negative 1. That's the only time we can't use this. So we should end up as, after the equal sign, so there is an integral sign here to say antiderivative of, but now that we have taken the antiderivative, now we're reporting what the antiderivative is. We don't use the phrase antiderivative of after the equal sign, right? This is now what the antiderivative is. It's x to the 2001 over 2001 plus c. Let's do this one. This one's a little stranger. First of all, the variable is no longer x, but is instead u. So instead of a dx, you have a du. I'm just trying to warm you up and get you used to an idea. So if the two u's here bother you, then change this u to an x and change that u to an x. But I think you're going to be all right. This, other than switching the u's to x's, it still doesn't fit the format up here. Like, we've got to be very literal. Like, you see how this is not in the denominator? Yet over here we've got 1 over variable to the, it's all in the denominator. So we can't apply the formula, at least not directly. We got to do something else. So what are we going to do? I think we should apply a little algebra first. We need to rewrite 1 over u to the third. Sounds a lot like some of the things we saw already, even yesterday, just in a totally different type of problem. But another way to write 1 over u to the third is u to the negative third in the numerator, right? Now this is an algebra step, right? The piece of replacing 1 over u to the third with u to the negative third is algebra. I mean, it's algebra done because we're going to apply a calculus process next, but the actual step is algebra. And therefore, I want you to notice this integral symbol and the du are both still written. So I hope this sounds like there's a familiarity to back when we did some derivatives, and sometimes we didn't differentiate right away. We're like, you know what? It'd be nice to rewrite something. Like, the kind of example I'm thinking of is when we needed to differentiate things like 3 to the power x plus 2, we have a new way to do this using the chain rule, but we actually looked at this kind of question before applying the chain rule, and we still kept our calculus notation, and did things like this. But because it was algebra, we had to still write the calculus notation of derivative. Same deal here. Now, having done algebra from one step to the next, we still need to write our our calculus notation. It's new calculus notation now, but we still need to write it. Now, though, the whole purpose of that is we have a problem that's in the right format. Just think of all the x's up here as being u's, right? And think about what n is, right? So n should be -3. So then, I think my arithmetic is right. I'll go with it's right here. U to the -2 over -2. Still plus a c. Don't forget that plus c. Right? If you take -3 as n and then you add 1 to it, -3 plus 1 should be -2. I hope that sounds okay. Okay, one more on this slide. Integral of x to the -1 dx. Now the problem is when n is -1, that's the one time we can't use this thing. So this does need to be remembered, but it's actually relatively easy to remember it because if you try applying this formula, you will end up dividing by 0. Right? If n is -1, then -1 plus 1, you end up with a 0 in the denominator. So we can't use this formula because n is -1. The formula only works for all other numbers. So what do? Are we stuck? Actually, to answer this question, you could write x to the -1 a different way. I want to remind you that another way to write that is 1 over x to the +1. So this question of antiderivative is what do you differentiate, right? Think of like how do we go, what do we start with to go forwards? Or if you start with x, 1 over x, how do you go backwards? And way back when, I want to see if somebody's willing to unmute and talk about it or willing to type about it. Like, what do you differentiate to get 1 over x? We had a derivative rule. ln, yeah. So ln of x, just to be a little bit more clear about the function, right? So I want to remind you that the derivative of ln of x is equal to 1 over x. And at that time, so we did this kind of initial derivative rule for logarithms, which was this, and then we looked at the more general one for any base logarithm, but we did have this thing, right? And in addition to this, this all we said at the time, but there's actually a little more information we can include. We didn't do it back then because it wasn't key for us right at that time, but I want to point out that if you actually, this is a function you differentiate to get 1 over x, but we had just kind of at the beginning of class explored this idea that actually there's many possibilities of functions to differentiate to still get the same result. So it turns out that if you, not just ln of x, but actually if you do ln of absolute value of x, this still works. And then of course we saw when you tack on a plus c as part of the thing you're going to differentiate, that plus c is going to differentiate to a 0 anyway. So this function, if you differentiate it, you still get 1 over x. I don't want to say a lot about why that is here in class right now. I do have a link that I'm not going to click on because the reasoning behind it is like it's a little much, I guess. So if you're curious, you can click on it or ask me about it later, kind of one-on-one in office hours or something like that. But the point is, if this is what you differentiate to get this, then we can swap these two. Of course, then we need an integral sign by swapping, and so I've got that written in kind of cleanly here. Right? So the integral of 1 over x dx is ln of absolute value of x plus c. The other thing to point out is you can, of course, where the 1 over x is, by algebra, replace that with x to the -1. So another way to write the same fact is integral x to the -1 dx equals ln of absolute value of x plus c. So now we're going to update this thing that we just saw a moment ago. So if you're ever given the question, integral sign, variable raised to a fixed number n dx, you should ask yourself, is that n, is that exponent, is it -1 or is it not -1? Now most of the time it's not -1, right? It's like you gotta hit the bullseye right on to get -1. So most of the time you have n is not -1 and you use the formula we mentioned before. This is the formula that undoes the power rule. But if you have this case when n is -1, then take a look at what we have right up here. That one special case that is not addressed with this formula it is addressed. We have it. Like we have. So I just copied this box down here. In fact, what I've done is I've copied the kind of the key. These two boxes here I've copied to the top of the next slide because I just would like to. I know time is short today, but I wanted to do a brief set of examples to illustrate. Okay, so you use this one if n is not -1, and then you use this one if n is -1. So for instance, you have antiderivative of x to the 6th, and so it's this one that applies, right? And you should get x to the 7th plus x to the 7th over 7 plus c. If you instead have integral 1 over x dx, first, in this case, I think what we should do is switch how the problem is written. So you'll notice there's still an integral sign like there was before, because this step is not finding an antiderivative yet. This step is using algebra to rewrite 1 over x as x to the -1. Having rewritten, now we've got this one doesn't apply, right? Because right now our n is -1. That's a problem. We have to. This formula only works when n is not -1. So when n is -1, we just get to quote the work from over here. This is really like this box has just been kind of, you could say, copy pasted right there. And just as a kind of note or reminder here, if you switch the variable from x's to u's, all the work is the same. So I just kind of didn't reveal in steps. It just copied that all from before. And then I have one final comment and then announcements. So this problem up here, there's one other way to write it. So it looks a little funky, but you can write it as integral sign, then the fraction, and dx in the numerator and x in the denominator. I know this looks totally strange, but the point is this dx thingy that's here and there. I want you to kind of think of this like a numerator quantity. I know it's a little strange. It's not very often we'll write like this, but it just occurs every once in a while. So I'm going to kind of just try to remind you of that each day. Just in terms of announcements, the key one I wanted to mention is it's a Thursday, so there's the online quiz, right? So please do the online quiz. Please drop by office hours, set up an appointment. I know that some things can be frustrating, but call the phone number during office hours if you don't want to use data. Let's get through this together, and I will see you next Monday. In fact, here's your warm-ups for Monday.